Hello and welcome friends. In this module, I am going to discuss use of tape for horizontal distance measurement in land surveying. As you learn the content, you should be able to use the tape for horizontal distance measurement as well as state the appropriateness of necessary correction and apply the same to obtain the correct measurement. My sincere request to all the listeners to refer this presentation in continuation with the earlier presentation, which is available for horizontal distance measurement by using CHEN. I have discussed a few things there. So, in order to avoid unnecessary repetitions, I am requesting you all. So, all these particular accessories I have discussed in my earlier presentation. Now, coming to the types of tapes. Here, the distances are very commonly measured by making use of some kind of tape with millimeter accuracy. As far as routine measurements are concerned, as far as precise measurements are concerned, tape is very versatile tool to measure the linear distances. Usually, this tape is wound in some kind of case with its zero end provided with some kind of hook. The kind of the tapes I have mentioned here, the tape could be linen, it could be of cloth. The problem is they become weight as well as they are not that accurate because subjected to stretching very easily. As compared to this particular linen or cloth tape, we can make use of plastic tape with more accuracy, and these kind of the tapes are available over the dimensions I have presented here. There could be glass fiber tape which is very flexible, strong, non-conductive as far as heat is concerned, and it is more accurate. There is a metallic tape which is fabric with interwoven metallic wires to prevent elongation as well as excessive stretching. Here, the accuracy that can be easily achieved is in the order of 1:1000, but as we go for use of the metallic tape, glass fiber tape, the accuracy can be had in the range of 1 in 2000 to 1 in 3000. Nowadays, use of steel tape is very common. As far as Indian conditions are concerned, that is standardized by IS code 1270/1962. There are a variety of the steel tapes which may be having 6, 9.5, 13, 16 mm width. Usually it is steel or stainless steel strip with thickness of 0.15, 0.2, 0.4 millimeters. The cross section is mostly slightly curvilinear. The accuracy by making use of steel tape can be easily had with 1 in 10,000 to 1 in 20,000, but it solely depends on the person who is using it. In addition, there is one more type of the tape which is called as Invar tape. It has got very low coefficient of the expansion. Invar is nothing but the mix of alloy. It is nothing but the alloy of steel and nickel. Steel percentage is 64%, whereas nickel is 36%. But here the material is very soft, and here it is subjected to kinking. Steel bands is one more old but helpful version which is available in some open framed reel case. In fact, here out of the figure that is shown here, it is nothing but open framed reel case. So it may have length of 10 meter, 30 meter, 50 meter, 200 meter, and having the cross sectional area more, it is more precise than steel tape. Usually, steel bands are preferred for measurement of baselines. This process we have discussed detail in our last presentation, very similar to the process that we adopt in order to measure the distance on flat ground or on sloping ground. Here also we can make use of this tape to measure the distances. Just to mention few of the mistakes which could be mentioned as common for using chain as well as tape, there are chances of the displacement of the arrows. One can fail to observe the position of the zero correctly. One may add or omit the full chain fully if that particular arrow is not collected or positioned properly. One may read from the wrong end, or the numbers could be read incorrectly, especially 6, 9. These figures creates the confusion if the direction is reversed while measuring. The numbers may not be called correctly, that's why entry could be wrong. Sometimes even people may read the wrong graduations, and even the booking of the entries could be one of the mistakes. When we think of taping, the surveyor must think about obtaining the results with high accuracy. That is, the degree of the accuracy should always be high. Hence, the standardization of the tape is important as far as the surveying measurements are concerned. Once again, my request is to refer our earlier presentation which elaborates the operation of the calibration as far as chain is concerned. The same process is applicable for tape also. So, the tape is usually standardized at the temperature of 20 degrees centigrade, or it can also be standardized at 27 degrees centigrade. It is expected to support fully for the length being measured. The tension being applied is in the range of 50 to 90 Newton, and hence under such circumstances it will give its designated length. It is better to avoid the use of tape in windy condition to avoid the mistakes and even involvement of some random errors. As we measure the distance, we can check its correctness against standardization, that is nothing but the erroneous tape length, or slope or pull and tension, applied temperature, applied tension and the sag caused because of it, even the misalignment. We'll discuss these particular errors subsequently. Just to elaborate, you know that in calibration process, the measuring means that we have is to be compared with some standard means or reference means which has got the designated length. So as you see here, the means that we are using is showing the length of 20 meters, but as we compare with our reference, there is plus delta L increment which needs to be corrected. Here, every 20 meter chain length or tape length that will be measuring will be shorter by delta L, and hence the quantity that is elongated, should be added for correction. So here we expect that tape has to have nominal or designated length under standard conditions. During our measurement operations, we ascertain its length. Here, the correction for the measured distance can be given by the distance which is measured into correction per tape length divided by nominal length. Here, the correction per tape length is nothing but the difference in between the actual length and its designated length or nominal length. If the actual length is more than the nominal length, the distance measured will be less than actual. Thus, error will be negative and hence the correction is positive and vice versa. The two shortness and two longness involved is also discussed in our previous presentation. Here, the error component can be worked out as E standardization is Lm into Ls minus Ln divided by Ln, where this Lm is nothing but the measured distance, Ls is the actual tape length, and Ln is its designated length, which is nothing but nominal length. Just I have given one problem here for your reference. Say for example, if the measured distance is of 4000 meters and the actual tape length when compared with the reference, it was found to be 30.01 meters, whereas its nominal length is of 30 meters. As we make use of this particular expression, we'll be able to work out the error component as 1.33 meters with its positive sign, being the actual length more. Hence, the correct length should be 4001.33. Here, the same concept can also be bit extended in order to correct the corresponding areas and values. Say for example here, the correction for measured area can be given by measured area into this particular bracket square. If the correction is to be applied for the volume, correction for volume can be given by measured volume into cube of this particular bracket. Accordingly, you can please check these particular calculations involved to understand the concept better. Slope correction already we have discussed. The measured distance along the slope will always be more. Hence, the error is always positive, and hence the correction required will always be negative. This particular slope correction is given as C is equal to the horizontal distance L minus this Lm, which is nothing but the measured distance along the slope AB. Here, as we determine cos theta, it has to be L by Lm. Hence, as we substitute with value of L, that Lm can be brought outside the bracket and Cs can be expressed as Lm into bracket cos theta minus 1. Somehow, if you have the difference in between the elevations as h, here that Lm square should be equal to s square plus square root of s square plus l square. So as we use this particular say Pythagoras expression, accordingly here we can determine this particular slope correction as square root of Lm square minus s square minus Lm. Here again I would like to add one more thing. Initially we considered that whenever the slope is ranging in between 3 to 5 degrees, we can consider the terrain to be flat, and we expect that no correction is required. Here, say if the measured distance is of 30 meter, if theta is 3 degrees, the CS works out to be 0.041 meters. Say if we consider the degree of accuracy for ordinary works as 1 in 2000, the permissible error is 0.015. And here the actual correction works out to be 0.041, and hence we have to take into account. So depending on the degree of accuracy, you will be able to apply the actual correction instead of simply relying on such thumb rules. Here if the height is of 1 meter, this correction for slope works out to be minus 0.02 meters. For this particular case, theta is 1.91 degrees, which is less than say 3 degrees, and as you see here the correction that is determined is quite negligible. Whenever we make use of any measuring means, maybe chain or tape, it needs to be fully stretched. That is, it has to be applied with design tension or pull. For ordinary circumstances, at least one should see that desired pull is applied so that it will be giving its designated length. Here, say, if the pull applied is more than the designed one, the chain, the tape that we are using will be elongated, and hence the correction will be positive. If the pull applied is not sufficient, the correction has to be negative. In order to work out this particular say correction, we can make use of this particular expression. E tension is equal to T minus Ts. Here this T is tension applied during the measurement. Ts is nothing but the standardization tension, which is design value. Lm is the distance that is actually measured. E is modulus of elasticity. A is cross-sectional area. Here the value of the modulus of elasticity for steel tape can be considered in the range of 1.9 to 2 into 10 raised to 5 Newton per millimeter square. Again, as you see here, say Ts, which is nothing but the standardization tension, is 65 Newton. Tape used is of 35 meter. Actual tension applied is 45 Newton measured by gauge, which is placed along with the tape. Tape weight is 10 Newton. The density can be considered for 1 cubic meter of the steel, and accordingly here we can work out the weight of 1 millimeter cubic of the steel. Correspondingly, here the cross-sectional area can be worked out and E tension can be worked out as minus 0.693 millimeters. One more correction that needs to be applied is nothing but temperature correction. Here when the tape is stretched, we can make use of actual set of thermometers, and accordingly we can measure the temperature during our measurement conditions. If the temperature is high than the design, then the material is subjected to elongation, expansion. If the temperature is less, it is subjected to the contraction. So, here the correction is positive when the main temperature during the measurement is more than the standardization temperature. Here, this delta T can be worked out depending on the design value and the actual value. So here, as the expression suggests, the length error due to the temperature change can be worked out by multiplying with C delta T, where the C is coefficient of the linear expansion and delta T is nothing but the temperature change. As you see here, one surveyor is holding the tape, another surveyor is holding the tape. If that particular tension applied is not sufficient, it will attain the shape of catenary. In simple words, it will be simply sag. So this sag correction, naturally because of this particular sag, the measured distance will be always more, and hence the correction will always be negative. Here, if the two stations are placed at different levels, their relative inclinity can be determined as theta, and this particular sag error can be worked out as W square ln(q) cos square theta divided by 24 t square. Here the expression can be referred with the elaborations given here. Hence, there is a need to obtain the true distance by applying all the corrections with their required signs. So here the actual length can be worked out by applying the correction for temperature, standardization, sag, slope as well as tension with their respective signs. Here, in order to understand this particular concept more, let's consider one example. So here the tape is steel tape, has got nominal length of 30 meters and it is suspended between the supports. Following observations were recorded. Here the standardization length is given, tape weight is given, cross-sectional area is given. We are expected to determine the correct horizontal length of the measured distance. So as you see here, this is standardization correction, this is slope correction, this is tension correction, this is temperature correction, this is sag correction. Hence, as we consider the worked out results under respective categories with the appropriate sign, we will be able to determine the true length as 29.823 meters. So, thank you friends. I hope the concept of type of the tapes, measurement of the tapes, corrections, need of calibration, etc. is clear to you. We'll continue our learning journey with the concept of levelings. So, I wish you all the best. Bye till my next presentation. I wish you very happy learning.